Welcome everybody on an unusual Friday afternoon or evening. Thanks for tuning in. Charlotte Aten is going to talk about discrete neural nets and polymorphic learning. Please.
So yeah, thanks so much for having me. I'm very excited to be here in person, and I actually didn't realize I was going to also be speaking for the first ever hybrid instance of PALS, which is very exciting. And as you can see, everything has gone perfectly. Yeah, thanks so much for having me. So today I'm going to be talking about this project, which is maybe a little more applied than what I usually do. I've been kind of drifting in that general direction, but I still identify as a pure mathematician sometimes, for whatever it's worth. And so this project has some overlap with a topic that people often discuss at PALS or adjacent seminars, which is polymorphisms. So I won't really have much to say about constraint satisfaction problems, but this will hopefully be yet another interesting application of the notion to something that people have practical concern with. So, okay, so to tell the story of how this project happened, I've been an instructor and organizer for this machine learning and data science REU at the University of Rochester for several years, since I was a graduate student there. And even this past summer, I actually went back, as I'm now a professor at the University of Denver. I went back to Rochester and continued to work on a sequel to a project which started at the same REU program in 2021. And so I have a new group of students now, and the preprint from the original iteration of the project is on the archive. These grayed out parts of the slide are actually hyperlinks. So when I share the slides, you should be able to just click them and get to the relevant things. You can see how it's been going. Oh, and there are links to these things as well. The code is actively being developed, so everything I'm talking about theoretically is in some stage of implementation. We do actually have some version of this learning procedure working and some at least toy examples. And as I was mentioning to Peter a little while before this talk, this is hopefully the prototype that my students and I are developing, which will eventually be inappropriately productionalized by other people. So you can watch in real time as it develops on GitHub. Okay, so first I'm going to just talk about how this project got started as far as the theoretical motivation goes. And that's going to be a discussion of universal algebra and universal approximation, which are not things that outside of my talks on these subjects, I don't think usually ever appear together. And then I'll talk about this notion of a discrete neural net, which is a natural generalization of the usual way that people think about neural nets. And then I'll discuss using polymorphisms of a relevant relational structure as the activation functions for such a neural net. And again, you don't have to worry if you don't already know what neural nets are in the usual applications, because I'm going to give a formal definition, which doesn't require that you know anything about neural nets as they have been done before. And then finally, I'll actually talk about this example, which kind of seems like a toy example about learning with just black and white images. But I'll mention at the end, without hopefully going into too much gory detail, that some results in my thesis justify that this is actually sort of the most general possible case of solving the problem of how to do this learning task. And so that's the motivation for the sequel that's going on now. Oh yeah, and feel free to interrupt. I think we're a small group, so feel free to interrupt with any questions if you have them. Okay, so yeah, so sometime during the 2020-2021 academic year, I was thinking about, I was thinking about machine learning and thinking about what kind of project I might want to organize for students. And I noticed that, some of the first really rigorous mathematical results about neural networks were these results about universal approximation. And they basically said, well, assuming that you're using a certain pretty general type of activation function for your neural net, and I'll define in my context what that means a little bit later, then your neural net could possibly, in theory, learn any possible function that you would like to model. And so that's good in the sense that that's in some sense a basic criteria that you would want for being able to perform a learning task, but it's also bad in the sense that often there are a lot of functions that we wouldn't like to learn, and this falls under the general paradigm of overfitting, as people discuss in machine learning applications, where the system, the neural net, doesn't know any better whether you mean to point at some more general trend or just tell it that only these few specific examples are these things that you're interested in. And so this overfitting really gets you because you often get sort of dumb answers to the types of modeling questions that you would like to ask a system like this. And so, okay, well, anyway, I noticed that there were similar results in universal algebra that basically, so Mirsky's theorem foremost among them, as you can see in the slide, that basically say, well, if you choose just pretty much any random collection of operations on a finite set, you can model or you can describe through composition any other operation that you would like to. And so this has a very similar flavor, and actually formally these are basically saying the same type of thing, because you can view a composition of a bunch of operations on a finite set as actually representing some kind of neural net where those operations are the activation functions. It's also interesting to note that Mirsky's result is actually older. It came before this work in machine learning, and I don't know that people ever made the observation that they were similar, but this type of thing happens all the time in algebra and combinatorics, where there will be some discrete result and the people on the analytic side will have sort of an analytic analog of it, and never the two will meet. Okay. And you can find my original video pitch for when I had an idea of this, but I hadn't fleshed it out as much, linked on that YouTube video. Okay. So then the idea, as I mentioned, was to use these activation functions that were just functions or operations on a discrete set instead of continuous functions. And my students and I quickly realized that even with a reasonable definition of how to do learning, you, of course, aren't going to have a nice analog of differentiability for discrete functions. This type of system would actually overfit really quickly, which was the same problem I was saying that the continuous systems had. In fact, it's actually even worse. And so what we realized is that using just any possible activation function is actually a bad thing, even though that is what people actually do in applications still for the most part. And so what we really wanted was to use activation functions which were polymorphisms of some relevant relational structure for the problem, because then the function that was modeled by our neural net would be a composition of these polymorphisms, and hence would be respecting whatever structure we imposed on the problem to begin with. And so it's really not, the application that we have in mind then is really not a very profound application of polymorphisms. The relevant fact is just that polymorphisms compose to give you other polymorphisms. Okay, so here's a formal definition of a neural net in the sense that I would like to talk about it. And so I think actually I may have a picture which is more informative than the formal definition, but I'll pop back to that in a second. So for a typical neural net, we're going to have some layers, which are these vertical arrays of circular nodes. And in each layer, well, we imagine that all of the layers past this first or leftmost one are, I guess I'll laser point at the screen for the people here in person. So this leftmost layer of the x1, x2, and x3, we view these as inputs. This is where we're plugging in arguments to the operation that we're modeling. And then these latter layers are viewed as being consisting of some operations, which have whatever number of inputs as there are arrows coming into the operation. And then at the end, there are some operations, but we also view those as actually being the outputs. And so this isn't really modeling an operation in the universal algebra sense, but rather a pair, if you want to think of it that way. Or in other words, this is a 3-to-2 operation, I guess, if you want to generalize your definition slightly. And you can see it as being the composite of these various Vij's with each other according to the picture there. And so a more formal definition appears here. We want some kind of digraph, which we'll call the architecture of the neural net. That's basically telling us how to compose operations together. And then we're going to have for each node, which is not one of these inputs, we're going to have whatever activation function appears there, or in other words, whatever sort of little operation we're composing together at that particular point. And we have a bunch of conditions about non-degeneracy, but that's basically the idea. Yeah, and please do ask any questions if you feel like I've been a little bit too vague. I don't know what everyone's background is. Well, okay, I do know what everyone's background is who's sitting right in front of me, but all right, anyway. Okay, so I'm not going to presume to know everything that you guys know, but I have some idea. So, okay, so we had this definition, and then, okay, so here by structure, this definition is basically just saying by a structure, at least in the context of the beginning of this talk, I just mean a structure in the sense of model theory. So it's a set that has a bunch of operations, n-ary operations, and it also comes equipped with some basic relations. And this is the setting of most familiar mathematics. I guess if you want to talk about limits or something like that, maybe it doesn't handle it quite as well, but most sort of classical mathematical objects belong to this general paradigm that people study. And so this is what people often call a relational structure. And the underlying set is the universe, and it has its various basic things. So these relational structures have homomorphisms. And I need to tell you what homomorphisms are in order to tell you what polymorphisms are. Although for this crowd, I won't belabor it too much because I'm going to assume that people probably have a good idea. So homomorphism just has to be a homomorphism with respect to the basic operations and also with respect to the basic relations. And so that's still similar to the universal algebra definition, where you just want that if you have a tuple in one of your basic relations, mapping the homomorphism over the tuple gives you a tuple that belongs to the corresponding relation in the codomain. Okay. And so then a polymorphism, well, naturally that's a higher arity homomorphism. And so it should be a homomorphism from whatever the nth Cartesian power of your structure is back to itself, where that nth Cartesian power makes sense because structures, according to that definition, form categories, and those categories have products. And so I'm allowed to talk about the n-fold product of a thing with itself. And then, of course, there may be homomorphisms between this a to the n and a itself, and those are polymorphisms, which are basically just n-ary operations, but inside of this category of structures that I'm talking about. And so probably this is familiar to people here or listening to this talk for PALS, but a group homomorphism from z to the n to z, that would be an n-ary polymorphism of just the group of integers. Okay, so we see objects like this all the time. And well, what is the object for which I would like to look at polymorphisms? What is the sort of underlying structure I'd like to use in order to do a learning task? So my sort of initial example is going to be that I want to consider polymorphisms of a graph, and the vertices of that graph are going to be the objects that I'm trying to do a learning task with. Those vertices are going to be n by n images whose pixels, so this is images in the sense of an actual picture, like in the computer, whose pixels are all either black or white. And that's what I'm calling a binary image here. Of course, as I'll maybe talk about more later on, a binary image in this sense is really nothing but a binary relation on a certain set. But okay, so I'd like to do a learning task with these black and white images so that my students and I can do things like experiment with the MNIST training data set that people use to test machine learning systems. And Okay, and so we want to preserve some natural notion of similarity between images. Certainly a reasonable function that takes images as inputs and gives you other images as outputs should probably not be affected very much if I were to, say, change a single pixel in one of the images. Certainly it shouldn't be confused whether I'm showing it a picture of a cat. If the picture of the cat is sufficiently large and I change one pixel, that shouldn't really change whether the system thinks that it's a cat. That would be a kind of degenerate behavior. And that's exactly the type of overfitting behavior that I wanted to avoid at the beginning. So we need a notion of similarity between images, and it's precisely that two images are next to each other or adjacent in this graph when they differ by at most 1 pixel. And that's said formally on the slide by saying that their distance, which is this Hamming distance, is at most 1. So it's just saying that if you think of them as relations, these two binary relations are next to each other when their symmetric difference is at most one member. They differ in at most 1 tuple. Okay, so I want to preserve this structure, so I need to find polymorphisms of this object. And some of these are easier to find, others are more difficult. So endomorphisms and automorphisms are relatively easy to come by. And this is where, when I gave this talk for the University of Nottingham, I drew some more pictures, but it's a little harder in this setting. And also, I think people probably might be more familiar with these ideas, so maybe I'll just say it. Well, the dihedral group acts on this Hamming graph, as I called it, for n by n binary images in a natural way. If you have a square image, then of course you can rotate it by 90 degrees or 180 degrees or whatever you'd like, and you can reflect it across its natural axes of symmetry. And if you do this to images that differ by at most 1 pixel, you'll get images that differ by at most 1 pixel. So you get endomorphism, or well, you get automorphisms of this graph. So those ones aren't hard to see. Also, any bitwise operation, like bitwise and, bitwise or, whatever you'd like, with a fixed image that you choose will give you an endomorphism of the graph. And so you can think about this in terms of the images as things like blanking out a certain area or filling in a certain area with all black pixels, or you can think about it set theoretically as taking things like unions, intersections, symmetric differences. And if you do that with respect to some fixed choice of an image, then you'll get an endomorphism of the graph. That's also relatively direct to verify. Okay, so higher arity polymorphisms are definitely a bit harder to come by. And so now I'm going to change my notation for the arity to be k instead of n, so that I can talk about images which are n by n and whose and then operations which take k n by n images and spit out a particular n by n image. And so there's a natural family which is easy to describe and parameterize, but which doesn't sort of have as much structure. And so that would be these so-called multilinear indicator polymorphisms. And so basically what this is saying is that well, this is basically the observation that if you had a function that took n of these pictures, or sorry, k of these pictures, and spat out another one way you can always guarantee that it will be a polymorphism is if the image of that map was only 2 possible binary images, say the image which is all zeros or all white, that's blank, or like the empty binary relation, and then something that has only a single pixel that is filled in, so like a binary relation that only contains a single tuple. And so any such map will be a polymorphism because it's trivial to verify that anything you get out, will be adjacent to anything else that you get out by applying the polymorphism. So, it's quite straightforward. So these are pretty degenerate. And in principle, I could actually say, well, I could define any possible function that I wanted to, whose image consisted only of the all white image and a 1 pixel image by just choosing any subset of the n by n black and white images to be the ones that get sent to the empty picture, and then the complement of it would get sent to the picture that has just one black pixel. So I could do that. The problem is that encoding that in a system that's going to be using lots of these things all the time is kind of expensive. Specifying an entire subset of the set of all n by n images in general is pretty expensive. I don't want to be sitting around choosing random subsets of this huge set of pictures. So there's a slightly easier to describe family of these things, which are the ones where you have that this little b is your choice of your image that has exactly one pixel, which is not white, say. And then these parameters ci are some fixed images. And then this dot product is just saying, look at the number of pixels that are simultaneously black in both of them, and then take that mod 2. So that is like the F2 dot product of the two images viewed as vectors over F2. And well, then you can multiply by an image by saying if your dot product is 0, then you just get the all white image, and if the dot product is 1, then you get whatever b little b was, which is some image that has only one black pixel. So that's a little easier to parameterize, since you can choose some random images for your coefficients, and you can choose some random pixel to use for b, and then that's a little bit easier to describe. But of course, a natural concern is that these might be a little bit too degenerate, and that's actually a question that we don't know the answer to. So so we do have examples of this system working, and we have examples of using these polymorphisms for our higher arity polymorphisms. But what we don't know is we don't know whether these are really sufficient to describe, in a typical real life case, to describe enough polymorphisms of the Hamming graph to be practically useful, because we've only done smaller test cases at this point and not larger sort of real life images that we might be concerned with. And so there is a more difficult family of polymorphisms to describe, which I think is also a lot more interesting. And that's actually a lot of the content of the paper that I linked before. But I think even though I'm doing pretty well on time here, I think that it's probably a little bit much to go through the definition of what these polymorphisms look like, but there is a much more challenging family to describe and realize what they are. And they're much more interesting than this. They have images which can be very large. And we actually have a systematic way of randomly generating these things as well. So it's actually something which is practically useful. And so, yeah, so that's what I say on this slide. The preprint contains a discussion of some even more involved polymorphisms. And so I'm also working with this year's group to extend these to higher arity relations. And we have a lot of problems which are both practical and theoretical related to this. So one of them is we don't know whether these more interesting to describe polymorphisms are necessary to generate enough polymorphisms of these Hamming graphs in order to do practical learning tasks. And this also is related to a theoretical question about what a nice generating set for all polymorphisms of the Hamming graph looks like, or what, you know, at least what's the difference between the clone that's generated by the ones that I've described already versus adding in the ones that I have just alluded to. So we don't know what practical import that will have yet, but it may have some. Of course, we wouldn't want to use the more involved ones if it turned out that they weren't practically necessary. But we suspect that they probably are necessary, but we're, again, not sure, either theoretically or in practical applications. And as I mentioned as well, we're also working to extend these to higher arity relations. Of course, there's nothing really special for most of what I just said about the fact that you're using n by n binary images, as opposed to, say, you know, n by n by n by n, you know, some higher dimensional arrays, if you want to think of it that way, consisting of only black and white pixels. it would be the exact same procedure for most of these things. Just use, the hyperoctahedral group instead of the dihedral group for the symmetries. You can define basically all of the same operations for higher arity relations as well. And now you can imagine some practical examples of why I might want to do that. Maybe I don't want to do image recognition or transformation for pictures that are 2D pictures, but maybe I want to do it on 3D, models or pictures of something. But there are some more interesting reasons that I would want to think about that as well. So, okay, so then I guess that's the last part I wanted to talk about. And I think maybe I will actually do something on the board since I have time, because I didn't do as many examples and I just talked at you. So let me actually discuss what I would like to discuss on the board, if that's cool. And then I did have some references at the end that you'll be able to see. So let me first find my mouse back to here. Okay. Oh, it's on the other screen. That's why this is a little bit awkward, but I'll get there. Okay. So so then the question is, why am I concerned with higher arity relations? Is it just for some sort of, just completely academic reason that I want to do this generalization? Well, as I may be able to actually write on the board here, what is it that I want to do? Oh, yeah, thank you. Oh, you got it? Okay. Thank you so much. Okay, so what is it that I want to do? And let me get myself a better piece of the board. How's that? Oh, is this? Okay, are we gonna find another camera that's better? All right.
But I don't know how to connect it to Zoom quickly.
Okay, so we're finding a better camera, I guess.
Maybe present, and is there a room? No, need HDMI. No, that's for present. Let's go back here. Yeah, let's go. Yeah, their room camera. Okay, maybe it's not worth trying for now.
Yeah, I think.
Yeah, well,
Yeah.
okay, thanks for trying, but I'll just make do with a smaller amount of actually this gets this whole board pretty well, so I think that that's perfectly fine. Okay, so so to remind you, the initial idea was to have some neural net like this, where these activation functions, these Vij's, were actually polymorphisms of this graph whose vertices, the things that I'm plugging in, were themselves actually, some kind of images. Who knows? Maybe this one's a star, maybe this one's a smiley face, maybe this one's, I don't know, a cube, whatever you'd like. We'd like to feed some kind of images like this into our neural net, pass it through some activation functions, and then we'd like to ultimately get some kind of result where we've transformed whatever we plugged in. Maybe I just won't subscript all of these. Where we'd like to get out some result, which is yet another image, which maybe we combine these and we get, I don't know, the image which is just all filled in. Why not? So we can do sort of binary classification tasks by just outputting images that are all black or all white. But of course, there might be more interesting applications related to transforming images as well. And so that was the initial idea. And then the idea of moving to higher arity relations is to say, well, these nice polymorphisms that we found that preserve similarity of pictures, those generalize to just similarity of higher arity relations. So we can imagine plugging in, instead of two-dimensional pictures here, we can just imagine plugging in some relations, which I could sort of view as higher dimensional cubes, but maybe let me just instead replace this with, we can plug in some phi1 that's a subset of, whatever our, or that's a, that's a subset of whatever our universe is to the, to the n, some p2, some p3. So we could plug those in, and then we could get out a similar kind of n-area relation. So, we get some, I don't know, we get some psi out that's still an n-area relation. And so, of course, that might just seem like something which is just an academic consideration, that it would be nice to be able to do higher dimensional things as well. Maybe beyond 3 dimensions, it seems less clear that it would have direct practical applications, just because, we don't often encounter things that visually look like higher dimensional objects in everyday life. But of course, the idea is that a lot of different types of data could be represented as higher area relations. And then what I realized, so actually I thought about this first, and then it took me embarrassingly long to realize I had actually proven a couple theorems in my own thesis that related to this quite strongly. And so what I had realized was that, well, first, that I should actually grab an eraser instead of trying to erase by hand. But what I had realized was that I actually proved in my thesis that if you wanted to work with some data type which was more complicated than just a bunch of n-area relations, well, you could imagine that you could think of a basic relation in some more generality as being maybe, maybe instead you want to take your relation to be, instead of a subset of like, a cubed or a to the fourth or whatever, maybe you'd want to describe something that was more topological, and you'd want to take a subset maybe of the power set of A instead. That's not a relation in the sense that people study them in model theory. Or you might want to look at something like the set A choose 2 that people consider in combinatorics, where I'm just looking at unordered pairs. That's technically not a relation formally in the way that people study it in model theory, although we can of course interpret this as saying we can look at maybe the adjacency relation that is a binary relation for the corresponding graph. But this itself really isn't a relation in the proper sense. And what I realized was that actually I had wanted in this part of my thesis to categorify this notion of having relations that could be given by more general functors. And so this is a categorification of the theory of structures that Bourbaki proposed in their series of textbooks, which they then just didn't use for the rest of the series, where they considered things that they called relations that were maybe like a subset of the Cartesian product of A squared with something like the power set of A cubed. They look at things like this and say, well, that's some relation on the set A. And I said something slightly more general, which was that, well, instead of only allowing these few basic operations like taking products and power sets, let's just instead consider the image of the set just under some functor. And so you'll notice this is also similar to the theory of combinatorial species. And so the result I proved was that if you make some nice assumptions, and okay, what I actually did was a little more general than that, because I didn't just use underlying sets, but underlying objects in some category. What I realized was that with some nice assumptions on what your underlying objects look like, that actually you always have the case that if you were looking at some structure with these sort of strange, relations, like maybe, your relation is a collection of unordered pairs from a given set, well, you can actually always unravel that into a bunch of higher arity relations by looking at the set of homomorphisms, from whatever relation or structure you're looking at into the thing that you're interested in. And then this is, of course, say the universe of this is B, then this will, of course, be a subset of, the set of all functions from B to A. But of course, you can view that as a size of B area relation on the underlying set of the original structure. And so you could do this for all sorts of different domains that you choose and get a bunch of higher arity relations that have data about the structure. And now, okay, that's just something which is a relatively trivial observation. The thing that was more involved that I did in my thesis was actually prove that under sufficient assumptions, this actually constitutes an embedding of categories from the sort of fancier structures that you came up with into these familiar structures from model theory. And so because of this motivation, it's actually reasonable to think that we could use polymorphisms of these higher arity relations to model precisely information about these more involved structures. And so that is to say, if I wanted to perform learning tasks on a more complicated type of problem where I had different types of conditions that I wanted to respect with my machine learning model, then I don't actually have to figure out polymorphisms for that type of object. I can use the polymorphisms that we've already been looking at just for n-ary relations instead of binary relations. And so that means that this sort of consequence of the Yoneda lemma in category theory is actually telling us that there's a systematic way of unpackaging more complicated data into a format which can be used in the type of neural nets that I've described today. And so going forward, my students and I are working on actually implementing some examples of this. It's not totally solved. This is the theoretical motivation. But now the question is, can we do this in a way that's actually efficient computationally for practical problems? All right, so I think that's about all I had to say, and I'm doing reasonable on time, right? So thank you so much for having me. Again, there's some references in the slides. Thank you.
Just gonna use your mic again. If any questions from the audience?